Okay. Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome to the VOC Matric Revision segment for Monday. Yes, it is the 22nd of August, and today we have Muntasir Kadri who's facilitating the lesson on physics, and the topic is momentum. And I'll hand over to him. And just also a reminder that this is a recorded session. You can always go back and view the lesson, inshallah. Please like and share. Assalamu alaikum, Muntasir.
Walaikum salam. How are you doing today?
I'm very well, alhamdulillah. And I will now hand over to you to proceed with the lesson.
Okay, shukran. Okay. Assalamu alaikum, everybody. So today we will be covering momentum for the physics paper 1. All right, so we'll be looking at questions related to momentum. So let's jump straight into it. So the first question, example 1, it states here, a simple rocket system consists of two parts. Parts A of mass, I'm pretty sure this is, okay, they're calling it 3m over here, 3m, and B of mass 2m. So this is going to be an algebraic question, right? As shown in the diagram below, B is stacked on top of A. So here in the first scenario, before the explosion even occurs, we have B stacked on top of A. So what does it mean? That means these masses are essentially together. Then in the second part of the problem, if we look over here, we can see an explosion occurred and it pushed A off of B. And we can see A is moving down with a speed of a third of the initial velocity that it went up with. Right? So the first question is, state the principle of conservation of momentum in words. So let's look at the official definition. And here it is. It states here that the total linear momentum of an isolated or closed system remains constant or conserved. Okay, so remember, if we look at this image, we can see the momentum is linear. It's just happening in the y-axis. Okay, and this is essentially occurring in a closed system. They're not saying that it's affected by friction, wind, air, anything of the sort. Okay, so that's what makes it essentially a closed system. There's no outside factors that can affect what's happening with this rocket. So that's the official definition. Now, let's go on to 4.2. They state ignore all external forces on the rocket. And they say calculate the velocity of B in terms of V immediately after the internal explosion. Okay, so let's go ahead and see if we can solve this one. So what I'll do is I'll just crop this image out, add it onto a new page. We'll put it here. I'm going to make it a little smaller so we have some space to work with. I'll go here. Just give me a second. Go back. And we'll crop out the question as well. Okay. Let's add this here. Here we go. Add to current page. Okay. So this is what we're looking at. Now, let's give it a go. So first thing you need to understand is that the basic equation for momentum is P equals M times V, right? This is the basic equation for calculating momentum. Momentum is equal to mass times velocity. Okay. Now, if we look at this problem, we have two momentums. We have momentum for this section over here, right? So we essentially have this momentum, momentum 1, and we have this momentum happening here, momentum 2. Okay. But if we look at this, right, this momentum here is basically the mass of A plus the mass of B times the velocity, because the masses are together. But here the masses are separate. But bear in mind that momentum is always conserved. So in P2, we can essentially say that this is going to be the mass of A times its velocity plus the mass of B times its velocity. So there's an equation we can use. So we need to set that P1 is equal to P2 since momentum is conserved. So we can go ahead and say that the sum of P1 is equal to the sum of P2. Now we jump into the problem and we substitute these formulas in. So we can write here, okay, if that's the case, that means mass of A plus mass of B times the velocity affecting both of those together is equal to this, not the sum, is equal to the mass of A times V plus the mass of B times V. Now, we substitute this information in. Mass of A and mass of B is 3m. So we can write here, okay, this is 3m plus 2m. And the velocity is just stated as V. And this is equal to the mass of A, which is 3m. We're going to times it by V, which is 1 over 3V. And we're going to add it to MB, which is 2m, times this velocity of B. Now, the velocity of B is not given. That's why we write velocity of B, because now we need to find it out. So we have to do some algebraic manipulation here. So we know that this is 5m times V is equal to, well, 3 times a third is just 1. So this is just straight up mv plus 2mvb. Now we rearrange the equation. We take mv, we move it over to the side, and we will get 4m dot v is equal to 2m dot vb. Now we divide by 2m, so this will just become 2mv is equal to vb. Right? And that should be our answer. Let's take a look at what the memo says. Was there anything else that we needed to do? I don't think so. Let's look at the memo. All right. And if we go down here, that's correct. That's correct. 2mvb, that's 1. 2 plus 3 is 5. Oh, did I make a slight error? Let me just check. Let me just check. We did everything correctly. That was right. Oh, sorry. Oh, yes, no, this is right. The mv goes over. That becomes 4mv. Right? Unless, let's see, mv, we take m out. Oh, I did make an error. My apologies. Let's erase this. Right. So we are right in saying this is 5mv. We are right in saying that this is just mv plus 2mvb. Sorry, I did something silly with my algebra. So this is 5m times v. And what we're supposed to do is remove m as a common factor. And this becomes v plus 2v. Right? Then we divide by m. Then this becomes 5v equals 3v. And this then just becomes, oh, sorry, make sure to state that this is VB. So we know then VB is just equal to 5V over 3. So 5 over 3 should be the answer. Let me just take a look. Or is it 3V? I believe it's 3V actually. Let me just double check the calculations. And here we go. So, okay. So I made an error. And that error was, we were supposed to say negative a third. Now, why did I say a negative third? This has got to do with direction. So if you look here, I forgot to take my downward direction as negative. Okay. And if I do that, we'll have a different answer. So if you look over here, right, we go back to the memo. We see that they said it's a negative a third V. So there it's moving down plus 2mv. Then this becomes 2m plus 3mv is equal to 3m times a negative a third b plus 2mv. Okay, this is then going to end up being a negative mv plus 2mv bf. Okay, and this is 5. And then we're supposed to take the negative over. And then we'll end up getting 6mv. And then we divide by 2m, and then we'll get 3v. And that shows us that our VB, the velocity for VB is actually moving upwards. And that makes sense. If you look at the image over here, this explosion occurred, pushed this down, and pushed this up. So it moves in the opposite direction. Now, let's look at the next question. The next question here, ignore all external that's the one we did. The graph below shows the average force exerted by A on B during the time interval, during the internal explosion as a function of time. So here we got average force versus time. Let's say name the physical quantity represented by the area under the graph. Well, if we think about how we have to calculate area, area is going to be equal to the force times the change in time. Now, what is force times change in time? Well, that is actually momentum. Sorry, not momentum. This is actually impulse. Impulse is equal to force times change in time. Right? And that should be the answer in the memo. Let's double check. And there we go. Impulse is the answer. Right? Now, let us look at the next problem. Okay. Then they state, redraw the graph in your answer book. On the same set of axes, sketch the graph of the average force that B exerts on A as a function of time. Okay. Is this for after or during the explosion? Let's see here. During the internal explosion. So this is during, not even after. Okay, so what's happening during the explosion? So we know an explosion is occurring. So let's think about this, right? There's an explosion happening in here, right? And that explosion forces B upwards and forces A downwards. So if you think about it, these two forces, there's a force acting up and there's a force acting down, right? So what does this mean? So that means that F2 is actually going to be some negative value, force 1 is going to be some positive value. And they are suggesting name the graph below shows the average force exerted by A on B, and that makes sense. This is the force upwards. So if you look here, we have positive values. Why? Because it's going in the positive direction. So here we can see, oh, at this time, you can clearly see this is where the force is happening, right? The force goes up, and then the force remains constant over a certain amount of time, and then all of a sudden that force has now ran out of ability to keep going, and then it drops and it decreases back to zero. Okay. So that means that for B, if they're asking here, where's this? Sketch the graph of the average forces that B exerts on A as a function of time, it's going to be the opposite of this, right? So that means the B is exerting a force on A, but the force is downwards, so it's going to go into the negative direction. So if we had to imagine this graph, let's just take this over here, copy it, add it to a new page. If we think about what's essentially happening on this graph, we're going to have another part of our axis, which is the negative aspect. Right? So here's our negative part of our y-axis. And what is basically happening is that B is exerting a force on A downwards, which is negative. So here's the force increasing in the negative direction. Right? So whenever it's in the negative direction, it's going to be a negative value. So here's it's going to be negative. Right? So it reaches a certain point, it carries on consistently for the same amount of time, and then it decreases back to zero. Right? And that's essentially what happens on this graph. If we take a look at the memo, let me clear this off. We can see that is what's happening over here. Right? Now, let's go on to example 2. State the principle of conservation of momentum in words. So let's look at the official definition. Linear momentum of an object is the product of mass and velocity. That's it. Linear momentum is a product of mass and velocity. And that is the principle of conservation of momentum in words. Now, sorry, not for that one. For define the term, that's the definition of momentum. I was saying conservation of momentum is different. Remember, it's got to do with conserving the momentum within a closed system. But if you're defining momentum, you can just look at the equation and you can see that linear momentum is mass times velocity. P is equal to m times v. Right? So the equation relates directly to the definition here. Okay, 4.2. They want us to calculate the velocity of ball Q after the collision. So let's look at this information that they give us here. Ball P of mass 0.16 kilograms moves east at a speed of 10 meters per second. moving east, right? So we're going to select east as positive, west as negative. Right? So we're only working in one dimension, which is along west and east, so that's fine. So we know this is linear momentum. Ball P of mass 0.16 kilograms moving east at a speed of 10 meters per second collides head-on with another ball Q of mass 0.2 kilograms moving west at a speed of 15 meters per second. After the collision, ball P moves west at a speed of 5 meters per second. Then as I calculate the velocity of ball Q after the collision. So let's first write down the information that's given to us. So what we'll do is we'll just copy this, we'll add it to a new page, we'll put it over here, and let us take a look and take down all the information that's given to us. So let's see, what do we have? We know that the mass, so we can, this is the mass of P, so we'll break it up into two parts. We'll write this part here before, right? So the information before. So before, the mass of P is equal to 0.16 kilograms. The mass of Q, okay, we can just get the velocity as well. The velocity of P is equal to 10 meters per second, and we're going to write it as positive. Right? It's positive 10 because it's going towards the right. Now we look at Q. The mass of Q is equal to 0.2 kilograms. The velocity of Q, because it's moving to the left, we say it's a negative 15 meters per second. Okay. Now we look at after. The mass of P remains the same. So I know this seems tedious, but trust me, if you are systematic about the way you lay out your information, it will help when you have to do the calculations. And then the velocity of P after the collision is 5 meters second to the left, so negative. Right? The mass of Q remains the same. It's 0.2 kilograms. And the velocity of Q is what we are trying to find. This is the unknown. So we are going to essentially have to use the conservation of momentum to solve this problem, where we state that the sum of P before is equal to the sum of P after. Now, let us go ahead and try to solve this problem. Now, if we look at B, what's happening? It collides head-on with another ball. That's what's going to happen. Okay, so we have this information before the collision. So the question is, do we have to add these values together on before the collision, or do we state them separately? Well, let's take a look. Ball P of mass 0.16 kilogram moving eastwards. Right, collides head-on with another ball. Okay, so we know it's colliding. And then this is the information after the collision. So this is before they collide. Okay. So if we just take a look at the memo here, I believe we're going to work them separately, and we can just double check that. And if we look here, that's exactly what we're going to do. We're going to work them separately. So let's do them. Go back here. Now, so we're going to state that the MP times VP plus MQ times VQ is equal to MPVP. So this is for after, this is for, and this is after, this is before, plus MQVQ, right? And I'll just state that this is for after, right? This is for after, and this is for before, right? So we know. Now, let's substitute our information in. 0.16 kilograms times the velocity, which is 10 meters per second. We're going to add that to MQ. So let's actually I'm going to need a little bit more space. We'll shift this over. So let's write this in 0.16 kilograms times by VP, which is 10 meters per second. I'll just write it like this for now. Plus M, which is 0.16 kilograms times by VQ, which is negative 15, is equal to, so this is going to be 0.16 times by VP, which is minus 5, plus M, which is, let me shrink this, move it out the way, here we go, plus MQ, which is 0.2, and the velocity we are trying to find, VQ. Okay, so let's go ahead and figure this out. Where's my calculator? So 0.16 times 10 is supposed to be 1.6. So this is going to be 1.6 kilograms per meters per second plus 0.16 times negative 15. Oh, sorry, this mass Q is incorrect. It's 0.2. Erase this. That's supposed to be 0.2. Here we go. That's right. So 0.2 times negative 15 gives me a value of negative 7.5. So I can remove this and just make it negative 7.5 kilograms per meters per second. And this is equal to 0.16 times negative 5, which is negative 0.8, plus 0.2 VQ. Right, let me put that in. Now we do some rearrangement. So let's see, 1.6 minus 7.5 is equal to negative 59 over 10 plus 0.8 gives me negative 5.1. So this is negative 5.1 is equal to 0.2 VQ. Okay. Let's just see if everything is correct. Yes, yes. That's negative. That's correct. We selected that. That's negative 5. That's correct. Okay. So this means that VQ is going to equal, move this out the way, is going to equal negative 5.1 kilograms per meters per second minus 1 over 0.2 kilograms. Now notice the kilograms cancel. That leaves us with meters per second. And that'll be negative 5.1 divided by 0.2, negative 25.5. So let's see how close we are. Are we correct? I really believe Q should have been moving in, to the right. I mean, if we did everything correctly, we selected our directions and everything, we should be on the right track. So let's see if we are. 4.2.1. Yeah, it's supposed to be positive. No, negative. Let's see. Yes, we stated that correctly. We stated that correctly. We stated that correctly. Did I make a mistake with my multiplication? Let's just go back. Is 0.16 times 10 is 1.6. That's right. 0.2 times 15 is 3. Ooh, that's where my error came in. So this is supposed to be 3, not 7.5. How did that come out as 7.5 on my calculator earlier? Okay, so this is negative 3. Right? Let's double check. 0.16 times 2. This is so strange. Why did my calculator give me weird values earlier? Okay, so this is 1.6. This is 3. Just double check everything. 15 times 0.2, 3. Yeah, that's right. 0.16 times 5 gives me 0.8. So this is correct. So this is where the issue is. Okay, so let's see here. So that's 1.6 minus 3 equals that plus 0.8 gives me negative 0.6 divided by 0.2. Yes, there we go. So that's right. Okay. So this is supposed to be 0.6 over here. It's only negative 0.6. Move this out the way. Let's erase this. So my apologies for that. For some reason, I must have inputted something incorrect here in my calculator. So this becomes negative 0.6 kilograms meters per second divided by that. And our answer, and this makes way more sense, is negative 3 meters per second. And that's basically 3 meters per second to the west. And that correlates with the information in the memo, which is perfect. Let's just go back here. Page. Here we go. Okay, and there we go. Negative 3 meters per second. So 3 meters per second westwards. Right? And let's look at the last problem. Let's scroll down. Oh, here we go. 4.2.2. The magnitude of the impulse on the ball during the collision. Okay, let's take a look at that. So remember, we said that impulse is F is equal to M times delta T. Right? So this is a little tricky because we don't have delta T, do we? We don't have change in time. So how are we going to go ahead and calculate the impulse on ball P during the collision? Well, if we go here, let's take a look. I'll clear this off. And we can scroll down. 4.2.2. So there we go. Impulse is equal to delta P. Delta change in momentum is another term for impulse if you need to know. There we go. And if net delta T is equal to delta P. So here we can go change in P is equal to M times, now it is change in velocity. So the final velocity of PE minus its initial velocity, and that's going to give us a value. So let us go ahead and we just take a look at the calculation. So let me just clear this off. We know this is negative 3, 4. I'll write this over here on the ball. This is negative 3 meters per second. So let us just clear this all off. And we can look at the magnitude of the impulse. So if net times delta T, or change in time, is equal to change in momentum. Change in momentum is equal to M times, so this is for P specifically, so mass of P times the velocity, final velocity of P minus the initial velocity of P. Now, let's take a look. So M, we know the mass of P is 0.16 kilograms. If we look at the final velocity of P, it's negative 5 meters per second. Right? And we're subtracting it from 10 meters per second, which is the initial velocity. So the change in velocity is negative 15 meters per second. So we can say, okay, 0.16 kilograms times by the change in velocity, which is negative 15 meters per second, is going to give us a value of 0.16 times negative 15. Oops, there we go, negative 15 is going to be negative 2.4 kilograms meters per second minus 1, which is the same as negative 2.4 newtons per second. Right? And that's our final answer. So 2.4 newtons per second to the west. And does it correlate? Yes, it does. 2.4 newtons per second westwards will be the answer. And there we go. So, as you can see, momentum and impulse, the important things to take into consideration. Understand your equations, what your equations for momentum is. Do not forget to place in your directions, depending on whether the motion is to the right or to the left or up or down. It's very important because if you forget those, as you saw with me, I made silly mistakes and my calculations were completely off just because I didn't take direction into consideration in the first problem with the rocket. Right? So very important. And then the other equation to remember is that F net is equal to delta T. F net times delta T is equal to delta P. So impulse is just another word for change in momentum. So remember, this is momentum, right? So just P is momentum, but change in P, which is basically P final minus P initial, is also equal to F net times change in time. And if you know how to alternate between these three equations, then you will be perfectly fine moving forward with momentum. Momentum isn't really a hard section, but yeah, just get used to using these equations and manipulating them. I promise you, you'll have a very easy time with momentum. So that is it for today with regards to momentum and impulse for today's physics session. If you would like to access these notes, they are available on the Intune website, right over here. I'll just scroll up. You can just go to www.intunetutoring.co.za. You can click on the home tab, and then on the tab, there will be a voice of the Cape link that you'll be able to access and view all this information and information with regards to prior lessons as well. So I hope this was helpful. Enjoy the rest of your day. Assalamu alaikum wa rahmatullahi wa barakatuh.
Walaikum salam wa rahmatullahi wa barakatuh. Shukran so much for today's lesson, and also reminded this lesson is recorded. You can always view, also like and share. From myself, Konita Kamar, and my guest this afternoon, I bid you farewell. Assalamu alaikum wa rahmatullahi wa barakatuh.